So I'm sure if you look at this, you're either gonna say, oh, this is easy to solve, or hell nah, I'm not solving that. But I promise you, if you watch this video, by the end, you will know how to solve a problem like this, and this one specifically. Or well, you can skip to the timestamp right here to see me solve it earlier, I guess. But yes, let's level up our solving of differential equations with lecture 30, these solving tricks. So today we will learn a few more additions to our differential equations solving toolbox. So separable equations is the first one, and it's basically when you can rearrange the equations so you have only the same variables on the same side, so all x's on the one and all y's on the other, and then just integrate that. Usually that's dy over dx equals xy. That's one of the examples. We've solved a couple of them so far because it's just simple integration. They're not much of a problem, but now we will know why and how, I guess. And then we have linear equations, so when we cannot separate, like the one we started off with, and we will introduce a new function and complicate stuff a bit to be able to solve it, but in the end we will get our result nonetheless. And lastly, this isn't really a method I'll cover today, but, well, we did learn U substitution and stuff in integrals. And since differential equations is 90% integration, I recommend you revisit those lectures and topics and read up on these fields like U substitution and trig substitution on your own, because I will not cover it today. I'm just saying it here as it is a method we could use to simplify harder differential equations. So let's start off with separable equations method. It comes in handy when we have an equation of such a form. So for instance, a derivative that equals a product of two functions where each function has a different variable. So basically x times y. I guess that's one way to write it. These are two functions. They're both linear functions, but that's one such example. Of course, these are other examples we could have. There's plenty more outside, and we will only be working with up to two variables. Well, only x's and y's. Okay, if there's any more variables, they will usually get cancelled out, or they will be constants, and we will just, yeah. So let's see how to solve such a problem. Again, we did solve some of them before, but now let's do it again just in case. We try to get the same variable to the same side. Here we have x and y, so we will move y to the left and x to the right. Why? Because, well, our goal is to integrate. And if we have dy in the numerator, then carrying the y to the left will make it easier to just integrate, because integration requires differential of the variable in the numerator. So dx will just be moved to the right, so it will be also in level here, kinda. So like this. And now that we have all of the same variables separated to separate sides, we integrate both sides and we get, well, that's how we would solve it. Then we would be left with some constants, and then we would use initial or boundary conditions. We could solve it completely, but more on the latter in a bit. So for our first example, we will solve the differential of y with respect to x, where that equals to x times y. So first things first, we separate the variables, and we know that if we integrate the left part, we get natural logarithm of y, and on the right, we get x squared halves plus c. Now, to solve for y, we simply anti-logarithmize. We get this, and this is one of our most common shapes we're ever gonna see. So, yeah. Some constant times e to the power of x squared halves, and that's it. Amazing and simple, is just integration. Now to our example number 2, let's separate the variables. Again, we move the y squared down, dx to the right, we integrate using simple power rule to solve it, and because, well, increase the exponent by 1, because it's y to minus 2, that goes to y to the power minus 1, and then we need to be like, oh yeah, divide by the new exponent, because it's integration, so we get this. And yeah, the right side just gives us x, and then plus c because we have integrations. We carry the y to the right, or isolate y, so it's like minus is on the right side, we get 1 over that, and we're left with y equals minus 1 over x plus c. This is it. We see that, here we can also see that changing the power, so xy to y squared changed the result itself, so the y value from cex squared halves to essentially minus 1 over x. So, this is a better demonstration or visualization in Desmos, where the red graph is basically the result from example number 1, and then the blue one from example number 2, where I only omitted constants, assuming they are 1 and 0 respectively. Well, at least I hope I did it right, because my brain's still fuzzy. Oh, and to explain, the exp function here, it basically means e to the exponent of whatever is in the bracket. It's an easier way of writing it, as you don't have to do superscript and then complicate with fractions and further exponents within the exponents itself due to the size of the position changes. So whenever I write exp x in physics, that's gonna basically mean e to the power of x. Hopefully this clears it out. Now we get to linear equations. And this is one such example. We have a derivative, some function p of x multiplied to y, that's only to the power of 1 because linear equation, and then another function r of x. The difference here is that these equations can't be separated, but still follow linear structure, as in the y being main variable and it being to the power of 1. Why cannot they be separated? Because we prefer a lot more a product of functions, so we would rather have f of x times g of x dx equals some h of y dy than we would having f plus g differential of x, kind of like that, because it's just a lot easier, or also even possible. So since the left side isn't a single derivative, as we have dy plus a p of x times y, it is not separable. So our goal will be to get single derivative on each side. How do we get that? We will refer to the product rule. So the product rule, which we may remember in the form of f of x g of x derivative equals to f times the derivative of g plus derivative of f times g. So this is how we were familiar with it in the derivatives lecture, but this is how we will have to be using it now. So the product states basically the derivative of the product is 1 times the derivative of the second plus the second times the derivative of the first. Since differential equations are basically the derivative of what we are looking for, so because we have to integrate, this formula should accurately represent this equation. So if we find a similar term, for instance, if we had a Pythagoras theorem where we have like hypotenuse as c and then like 4 and 3, we could write the theorem itself as a squared plus b squared equals c squared, and then for the triangle we would write it as 3 squared plus 4 squared equals c squared, and we would be like, oh, these two are equal. This means that let's say these two are equal and these two are equal, for instance. So in this case, if we find some similarities, we can basically just equate the respective terms. So we would get 3 more equations. So one part that we know is identical because, well, yes, and then 2 parts where we can solve for the unknown parts, subparts. How do we do this? Well, yes, I will introduce a new function and multiply the equation with it. This new function, marked with Greek letter mu, basically Greek letter m, and we will multiply it to every single term in our equation to get this. So basically we just added mu to every single term. To be fair, it should be mu of x like it's here, but I'll only use mu to avoid burning you out with more symbols. Now we need to match our functions with the product rule. So I will replace u with mu, that hurts, and v with y to get this. Now we need to find out which part is which, and I can already see that these, oh god, I cannot draw, and this are identical. So that means if we add something to that part, so this or this, these two should also be identical. And of course, following that, the result should also be equal to the result of the other one. But yeah, so I'll write out the purple part first and solve for mu to get the value of the function that is described as mu. So I equate the 2 parts. I cancel out the y's on both sides as well, because, well, these 2 parts are equal and y is a function that is not 0 always, or always not 0, sometimes not 0. Sometimes 0, but not always. Anyway, and this is our new condition, so our new differential equation, which we can easily solve for function mu. We carried one variable to one side and the other to the other side, and we get our familiar formula of natural logarithm of something equals integral of a function plus c. And then we reshape that into the value of mu function. Now, a quick note, we leave the integral here as this is the general rule and we don't know what form or shape the integral might take. Because of that, we know that we will get another constant, and because we will get that constant will be put and multiplied to the e where c is now, which means that, because like after this integral is solved, we get e to the power of integrated function plus another constant, let's mark it as k, which means we will get e to the power of f times another constant, because e to the constant is like another constant. So just here and only here, we can omit the constant multiplied. Okay? Because we will get it back as there is another undefined integral there, and we minimize the amount of factors to remember, you can write it, you can leave it. It's crucial that you know that this is allowed here, especially because we have one more integral on the right side, which will lead to that constant returning when we solve it. Also, sometimes it just cancels out. I thought it's important to add as the constant will be present, but it's unnecessary to add right now, as it should come back if we do everything right. Now, this is it for the purple part, but we have one more, the simplified equation for blue part. And this is an easy one. We carry the dx to the right side and basically integrate. Whatever is inside the brackets here becomes the result on the left. And on the right, of course, again, there should be a plus c, but again, we have an integral that will give us the constant that we will end up combining, so we don't need the constant right now. And now we have the equation for the product of mu and y, and we have an equation for mu, so what do we do to solve for y? We divide the blue part with the purple part. Of course, we solve for the value first. Also, you can just insert it as well, because, well, the y is the result. But yeah, sometimes you can solve mu first and insert it. Sometimes you have to insert the function. Sometimes you divide whatever is the easiest at that moment. But I'll show you that on an example. This is the general rule, so this will always be useful. You can remember this, you can memorize this. I do recommend you at least know this, how we got this. So if you know how we got this part from this part, then in my book you're already a winner, you already know this. That's the point of maths, to get from point A to point B. In this case, you can remember the point B result and then apply it to every problem as it goes, but I guarantee you, if you know the origin, so the point A, the process from point A to point B, it will be so much easier for you to solve any example I throw at you. I guarantee you that, because I have a subject in which the professor is like, oh, yeah, you need to know the basic formula for temperature and heat transmission and heat resistance, and you will use those with, and then make a differential equation 1, and then use another differential equation for the shape of an object. And after that, you will have to create a specific formula that's only fitting to that exact problem we have. So it's pointless to remember the final product. I have to remember the process, what we did in each step, how we solved it. So this is what I try to teach you guys, so you know how to get from point A to point B without knowing what point B necessarily is. Kinda. So, on to our example. Well, we could have solved it the old way by just moving 2y to the right and then dividing by y or something, but let's try to overcomplicate it with the new method. And after this example, we solve the one that I promised at the start. So let's get our mu function first. We just put it in, we don't have to know it yet. Now, if you want to do this the long way, you can just write out the derivatives formula, the product rule and everything, and then connect the terms together. But I see that one of the terms has y here, so I will connect the y d mu over dx equals of this entire term, because this is the general part, so like from before here, this is the general part. So I will equate the whatever we did there, so the product rule on the left, so product rule, and the general form on the right. and then I'll just fill in what I have. So we have mu, okay, we have y, perfect. So our p of x must be 2. So like this. Oh, sorry, minus 2, because, well, there's another minus in between them. So I fill that in, and now we cancel out the y's, and simply move mu's to the same side, integrate, and we get this, solve for mu anti-logarithmate, and we get this. We could have just inserted it into the formulas and got it on the, like the formulas we got before, but it sticks better if you go through the dirt yourself and know why it is the way it is, which is very important for differential equations, as this is the one field where you can't and shouldn't try to remember solutions, but rather try to understand the process of what you're doing, as I just said before. So, we got the purple part, so the function of mu. Now we equate I can't speak, the product rule part and the right side of the general form. So the differential of mu y equals mu times r of x dx. Now, on the right, we see that we do not have a mu because, well, r of x is 0. So the entire right side becomes a 0. Now, technically, we could have dx here, but it's pointless because nothing changes. So we only have an integral on the left side. We can simplify it by inserting mu directly in. So like this. We can integrate, and this is basically the f of x. So the result of f, like, we just get f of x as the result, meaning everything in the brackets is the result, and then plus c, because we integrated. And then we get this. Now to solve for y, we simply carry the c to the right and divide with everything else but y. And we get this. This is a painful answer, so let's simplify it slightly further. Something to the negative exponent means it's in the denominator. So we have e to the minus something in the denominator. We can move that to the numerator, so up, and the exponent becomes positive, like this. And now we have a constant c divided by a constant k, and even a minus in front of it. So we combine all three of them into a new constant. Since those values will not change and it's pointless to overcomplicate it with various constants we need to solve for, we can simply say that y is some constant times e to the power of 2x, which if we solve the easy way we would have gotten faster, but why do we have this method? Well, for the next example, the one I cliffhangered you at the start of this video. This is our problem from the start, so let's see how to solve it. First things first, I will move the y to the left, so we have the differential of y and y itself on the same side, as we did in the general form. Now, we need to multiply each term with the integration factor mu. I'll write as the product rule here, just so we don't have to jump back. So like this. Now, let's think how to solve this. First things first, again, remember the product rule and assign which term is which. We see mu times the slope is mu times the slope. These two are the same. We compare the terms and sides, and we see that these two orange ones are identical. So I'll call these parts anchors, because they are identical. So it's like a factor 3 minus something, and then 3 plus something. I can refer to such things as anchors. That's not probably the right way to call them, but for me, it's just a reference point that connects two equations. So from that, we will say that the purple parts must be equal as well. So I will write out that equality right here. We will first cancel out the y's and separate the variables and integrate. And now we have the familiar natural logarithm shape, so we just anti-logarithmize to get the formula for our integration factor mu. And this is it. This is it for this problem. We will write it on the slide as we will need it in 1 or 2 steps. And now we need to equal the blue parts. We get the differential of this equals mu x. And in the latest equation, we will insert our integration factor formula we got a few steps ago. So instead of dividing it, I will just insert it, because if I had conditions, I could technically solve for the constant and then insert it and just calculate it, but nah, that's fine. The insert is usually simpler. Now we have a single derivative on the left and a single factor on the right, so that's perfect. That way we can readjust the differential of x to the right to get two integrals. And now we simply integrate. Left side just becomes the left side, as we remember the rule for integration of the differential of the function, while the right side stays tricky. Before we solve this, I'll just simplify. The c constant, We have a plus k constant from integration on the left, because technically it is different. So I will divide both sides with k to give us just one constant. So, or I can divide by c to get these c's cancelled out. So we get k over c, and that's gonna be a. It's just a constant we will solve for later, so we don't have to be like, oh, c times k divided by b times c1 to the power of k, and this is all e to the power of this, and it's all constant. No need to complicate it, just one constant, which of course we will still add something more. Now, for the right side, we have an integral of product of two functions, so we will use integration by parts, which, if you aren't familiar with, we covered in lecture, that was 27, at like 22 minutes and 43 seconds. That's the exact timestamp I looked at. In case you forgot, I'll give you the formula on screen. So here we need to determine which part will be u and which one will be dv. So which one are we integrating and which one are we taking the derivative of? For that, we followed the Linear rule, which helps us pick what function is u, and it means logarithms, inverse trig, algebraic, trigonometric, and exponential. We see that x is algebraic and e to the minus x is exponential. A is before e, so, well, everywhere except for EA Sports. So x will be u and the rest of the integral will be dv. So let's clear it up and make it easier to solve. So I just clear it up, give us the formula here. So this is the by parts. This is the problem we're integrating from here. We assigned the a and e to get u and dv. So I just moved the right part that we're solving right now to the right. Next step, we need to differentiate u into du and then dv integrated into v. So we write the differential of u over dx equals x. Sorry. On the right side, we get dx over dx, and that's 1. And then we move dx to the right, and we get this as du equals 1 dx. And if we integrate this one, we just know we divide by this a in front, so minus 1. So we get our v. These are simple integration rules. We can check that lecture back if you want to, but that's something we already know by now. Is that it? Yes, it is. Now that we have all 4 building blocks, let's insert them into our formula on top. So orange is u, blue is v, purple is du, or yeah, and then dv is white. So this one goes here and here, blue one goes here, and purple one goes here. And then white one goes here, but that's insignificant. So this is the part that matters to us. We're integrating, so I carry this up. I write this out. I will color everything white so it's easier to solve, because, well, too many colors also hurt our brains. Now we need to integrate the minus e to the power of minus x dx. And we will use the same rule we did to get from dv to v. And we divide with whatever is multiplied to x in the exponent, and that's minus 1, so the minus will disappear. Well, the result will be e to the power of minus x plus c, and then because there's a minus in front of this is gonna stay minus, and this should become minus, but constant is easier to just leave it as a plus. So this is a minus and a plus, so we're gonna be left off with a minus. That's all that there needs to be known. Now we factor out the common factor, which in this case is minus e to the power of minus x. We get this. I don't know why this isn't colored green, but yes, the minus here. And then we're left with x minus 1, plus 1 plus c. Do not forget there's a minus here. But yes, this is the result of the integration here. So let's move this to the left rectangle. So the red part to the red part. I will insert it. I will clear the right side of the board. I will extend it all to the right. And now that we have our almost solution, because we solved all the integrals, we move the constants to the same side and label them as k, for instance, because it's just easier. Next up, we have e to the power of minus x on both sides. So let's divide the entire equation with e to the power of minus x. Or, well, we could multiply by e to the power of x, because this just means that it's 1 over e to the x. That's what it means. So basically we cancel these out and we get a e to the power of x next to the constant. So we're left with this. Now we just like reorder slightly and remove the brackets. So this one will be the first factor for fun. And then we have minus x minus 1. And we get our solution for the y function. This is it. So for the differential equation of the derivative of y with respect to x equals to x plus y, the problem I cliffhangered you at the start, the function is equal to some constant times e to the power of x minus 1. And we see that all it took was some basic integration by parts, and the product rule for differentiation, which, to be fair, is quite a few things, but we know all of them. We covered all of them in like 2 different lectures, the recent ones. So this is proof, again, that my lectures can help you get the basic knowledge to solve certain examples. But yes, now we have successfully solved the equation we started the lecture with. So now let's learn some cool stuff to help us solve even harder examples. So in the last lecture, I mentioned initial conditions. As the name suggests, initial conditions are referring to starting conditions. Like at time is 0 and the time is the one that varies, while boundary conditions refer to spatial conditions, and while position will be the variable changing more often than not. Anyway, it goes that at the end of the day, both are conditions, and those conditions are basically used almost the same way when it comes to solving. So technically you don't have to call them initial or boundary. You can just call them conditions. And because they're like, what is the value of the function at certain other value? So that's it. A generalized way to write initial conditions is that the y at some x0 is y0, while a boundary condition is the one that the value of y at some xa will be a, where the xa refers to some non-zero position. We see that technically they are the exact same thing. One is just the name for the beginning position or position 0, while the other one is at every other time or position. But yeah, now to a real-world example. Well, technically not yet, but one such example would be a rod or a wire that produces heat, and it is surrounded by a layer of insulation. Radius 1, so the inner one, refers to the radius of the part that's heated, so the wire that's producing the heat, while radius 2 is the radius 1 plus the extra distance that insulation provides. So we could have an initial condition in regards to distance where radius equals to 0. So radius will be radius 0, which is 0. And that's where the heat originates from, so that's where temperature is going to be the highest. We could have boundary condition 1, so the first one, where the radius equals to radius 1, and the temperature equals to temperature 1. So at that distance, what the temperature is, that is the contact point between the two layers. For example, at the radius 2, so when the radius is radius 2, temperature would be temperature 2, because that's the contact between insulation and air. And we see that this gives us 3 positions. So our differential equation would be able to be a second-order differential equation, and we could still solve it. Since double integration gives us 2 constants, we could solve for both. Plus, we would have an extra condition to solve for any other constants not given. We may even solve that example next time, and I'll show it to you after we solve the theoretical example. So, example 2, or the first one actually solved. Last time we had an initial condition, and we wanted to know the formula and the value at the desired position or time. Now we will get the boundary condition and solve for formula. The process is basically the same, just different values. So by now we know how to solve this. We move the x to the right, integrate both sides, and we get this function. Now we use boundary conditions, so when x is 2, y is 5. So 2 squared is 4, so we have 5 equals 4 plus c. So yes. And then 5 minus 4 is 1, so c is 1. So we insert it into our function, and this is it. This is our final solution for this example. It's easy. It's literally initial conditions, just not zero. Now, for honorable mention, at least for now, this is an equation I recently had the displeasure of using in one of my classes, although it's easy when you have certain experience using them. Basically, how temperature changes as radius increases in a cylindrical system. So in a cylinder, so like this, that's a horrible cylinder, you take a cross-section, which is a circle, like we did before. The further out you get, the less hot it should be. This formula describes that, and in my class, we had to integrate it. Of course, there was slightly more to the equation, so it was something like this. You don't have to know this. This is just me yapping about fun facts and honorable mentions. So we had an extra term for produced heat. So for the heating element explained 2 examples ago, the center that produced heat had this term present. The insulation around it didn't. And all that equaled to 0 for the example we had. You had to move the r, so this part, rdr to the right, integrate first time, get a constant, then move the second dr, because after we're left with like k dt dr equals to some this integrated r dr. This is already solved, by the way. This is like a capital R function, radius, whatever, plus c. Then we have to move the second dr to the right and integrate again. Solve for both of the constants at any time you had boundary conditions, and you get a function of how temperature changes with radius, and previous temperature, of course. So for instance, our initial condition was that at radius is 0, so the center, the slope of the function of temperature in regard to radius was 0. Now what does that mean? We remember from derivatives that when the derivative is 0, we have either a maximum or minimum. So if the center, where r is 0, is producing heat, that's where the highest temperature point should be, and all points after that should have a lower temperature. So that's how we determine that the highest temperature place must be a maximum, and we can write that just as a derivative, since that's the same derivative is present in our equation, like here, so we could easily solve for one constant after first integration already. But as we see, we have a derivative of a derivative, spatial dependence, physical constants, so it looks a lot more complex, but it is built on the same ideas, rate of change, relation between variables, etc. And through knowing the system, we can determine certain boundaries or initial conditions that aren't given. We just know that the wire in the center is heating, so the sphere, and then like the outer is insulation, and then inside is heating. Just by knowing that the inside is the heating element and the outside doesn't have the heating, we knew that the maximum point, so the derivative 0, must be in the center. So if you read the system, you can already get certain conditions out. Through that, we can determine conditions, boundaries, and that can help us solve this equation without many problems. I'm not going to bother you with this example yet, as we just learned 2 new ways to solving differential equations, but we may solve it in the next lecture, and if we don't, we will definitely run across it either in physics, chemistry, or just some shorter educational video, so apologies for rambling and confusing you before with no writing on screen and whatnot, but I'd rather not overload you. And here is the mini test. I wish you best of luck solving it. It's nothing hard, it's basic integration here. We use the integration factor here, so the linear equation thingy, and then this one, the second problem here is the boundary condition, or in this case it's initial condition, so the same thing, but yeah. But this is it. Thank you so much for tuning in today. I hope the mini test solving goes well. I hope you learned anything new. I hope you got certain knowledge, certain inspiration to pursue maths more on your own. And thank you again. And I'll see you all on our next quest. Bye!